So to introduce the concept of limiting reactants, let's take a look at a scenario you may have encountered in life, or at least one similar to it, a scenario that takes you no further than your very own kitchen. So in this problem, we're going to talk about how to make the perfect gin and tonic. So I say there's nothing better at the end of a hot summer day in Modesto than a gin and tonic. The classic gin and tonic is made over ice and contains 1 ounce of gin and 8 ounces of tonic water. A twist of lime is always nice. We could write this recipe in the form of an equation as follows. That is 1 ounce of gin plus 8 ounces of tonic water yields 1 gin and tonic. Now let's suppose you're having some friends over for drinks, because you're over 21 of course, and you want to serve gin and tonics. If you have a nearly full 2-liter bottle containing 64 ounces of tonic water and a 750 milliliter bottle of gin, okay, which converted into ounces is equal to 25.4 ounces of gin, how many gin and tonics can you actually serve at this gathering? Well, let's think about this. With 25.4 ounces of gin and only 1 ounce of gin required per gin and tonic, you have enough gin to make 25 gin and tonics. If we turn our attention now to the tonic water, we see that with 64 ounces of tonic water, but with 8 ounces required per gin and tonic, you would have only enough tonic water to make 8 gin and tonics. So you see that the total number of gin and tonics you can serve is limited by the amount of tonic water you have. Tonic water is what we would consider to be the limiting reactant in this equation, because it is the reactant that limits and determines how much product, that is, how many gin and tonics, ultimately can be formed and served. The other reactant, that is gin, is what we would call the reactant in excess, because there will be some gin left over after all the gin and tonics are produced. If you can produce only 8 gin and tonics because of the tonic water being a limiting reactant, okay, then that means that you are only going to end up using 8 ounces of gin. So if you start out with 25.4 ounces and you use up 8, you will be left with 17.4 ounces of gin after all the gin and tonics have been made. So whether making gin and tonics, cookies, or 3-bean salad, you've probably encountered this concept of a limiting reactant before. That is, one of the ingredients in your recipe will limit the total amount of the recipe that you can make. This concept applies in the chemistry lab as well as the kitchen. The idea that very often one of the reactants, because of how much of it you start with, will end up limiting how much product can be formed. So let's formalize the concepts introduced in the previous slide by defining what we mean by a limiting reactant and a reactant in excess. So a limiting reactant, and we will abbreviate it with the letters LR, to save us a little bit of time. Limiting reactant is the reactant that gets completely used up in the chemical reaction and limits the amount of product that can be formed. The reactant in excess, symbolized RIE for short, is the reactant that doesn't completely react and is left over at the end of the reaction. Reverting back to our gin and tonic recipe, you see that if we had exactly 8 ounces of tonic water and exactly 1 ounce of gin in our house, then we would be able to form exactly 1 gin and tonic. we would refer to this situation as having stoichiometric quantities of reactants. In other words, all the reactants would be completely used up in the reaction. We would start out with exactly the right amount of each reactant, okay, so that at the end of the day, there would be none of those reactants left. But in real life, very often, we don't start with the exact amount of each reactant required to form the products. So in such a case, we need to figure out how much product we can actually form. In this slide, I'm going to outline a procedure for how to solve the stoichiometry problem involving limiting reactants. In other words, a stoichiometry problem where you do not start out with the exact right amount of each reactant to form the products. I want to point out that this is not the only procedure, this is not the only way to go about solving such problems. If we had more time in the course, we could talk about other approaches as well. But because time is limited, we'll stick to this procedure, which, by the way, will work perfectly well, okay, while being fully aware that it is not the only way to go about solving such problems. So let's talk about the procedure here. The first step, as with any stoichiometry problem, is always to write the balanced chemical equation for the reaction. Once the balanced equation has been written, okay, we need to convert the mass or moles, whichever is given to us in the problem, of each reactant into moles of product. So this is the approach we're going to take to determining which reactant is the limiting reactant. Now, different problems will give you different units for the reactants. If the reactants are given to you in mass units like grams, then it is first necessary to use the molar mass of each reactant, okay, to convert those masses into moles. And then, as we saw in the last lesson, you can use the ratio of coefficients in your balanced equation to convert the moles of reactant into moles of product. So once this is done for all reactants, the next step is to determine the limiting reactant. It turns out that the limiting reactant will be the reactant that produces the least amount of product. So all you have to do from step 2, okay, when you look at how much of a given product each of those reactants can produce, the reactant that produces the least or smallest amount of product will be the limiting reactant. Next, we need to answer the question based on the limiting reactant. Now, different problems will ask you to find different things. Okay, but the typical stoichiometry problem, okay, will ask you to find out how much of a given product will be produced. Now in step 2, okay, in 3, you found out how many moles of a given product could be produced. So you may be able to answer the question in the problem. But, okay, you may have to take the additional step of converting the moles of product to mass of product, okay, using the molar mass if that is asked for. Okay, the other thing that is very often asked for in these type of stoichiometry problems is for you to determine how much of the reactant in excess is left over after the reaction is complete. So here's a little flow chart that will sort of outline a procedure to help you determine this. Okay, the moles of product formed from the limiting reactant, okay, you know that from steps 2 and 3. You can then work backwards using your ratio of coefficients to find the moles of the reactant in excess that will be consumed. Okay, once you know the moles of reactant in excess, okay, that is consumed, okay, you can use the molar mass of that reactant to convert it into grams. And once you know the mass of the reactant in excess that's consumed, okay, then very often you can perform a subtraction problem to figure out how much of that reactant in excess is left over after the reaction. So let's take a look at applying this procedure to a couple of examples. In this first example, we're told that the reason that silver tarnishes in households is due to the presence of small amounts of H2S, okay, that is hydrogen sulfide, a gas smelling like rotten eggs that results from the decay of food. The black tarnish you see is a compound called silver sulfide. The chemical reaction can be described as follows. Okay, you can take a look at it. I won't read it to you. If the surface of your silver teapot has a mass of 125 grams and 13 grams of hydrogen sulfide is present, what mass of tarnish is produced? What mass of the other reactant remains after the reaction? So here is a typical stoichiometry problem, okay, involving limiting reactants, where we're given certain masses of each of those reactants, and we need to figure out, okay, which of those reactants is going to be the limiting reactant and is going to limit how much silver sulfide can be produced. So let's follow these steps, starting with the balanced equation. I'm just going to rewrite that equation because it's given to us in the problem. Okay, so that was rather easy. Step 2, we need to convert the mass or moles of each reactant into moles of product. Now here we see that we really have 3 reactants, but we're going to assume that the oxygen in the air is of course a reactant in excess, because there's always plenty of oxygen in the air, and also because it wasn't quantities of oxygen were not given to us in the problem. Okay, we are given, okay, quantities of silver and quantities of hydrogen sulfide gas, okay, in grams. Those masses of those reactants are given to us. So we're going to convert the mass of each of those reactants into moles of product, okay, using some stoichiometry. So here, as we said in the previous slide, okay, using this flow chart, okay, the mass of each reactant will start with silver. We've got 125 grams of silver. We'll use the molar mass of silver to convert that into, okay, moles of silver, okay, the moles of the reactant. So here we will arrange our molar mass this way so we cancel out the units of grams. Okay, we're then going to use the ratio of coefficients to convert the moles of, okay, a given reactant into the moles of product. So here, okay, from our balanced equation, and the product we're interested in this problem is silver sulfide, not the water. So let's see how much silver sulfide is formed. Okay, so using the ratio of coefficients from our equation, we see that for every 2 moles of silver sulfide formed, okay, 4 moles of silver is required to react. Okay, notice here that, okay, our unwanted units cancel out, so at the end of the day we're left with moles of the product silver sulfide. We do the number crunching and we come up with 0.579 moles of silver sulfide produced from a starting quantity of 125 grams of silver. Let's go through the same process with the other reactant that we're interested, that is with the hydrogen sulfide. So there we're starting out with 13 grams of hydrogen sulfide. Okay, we will once again divide by the molar mass to convert from grams of hydrogen sulfide into moles of hydrogen sulfide. Okay, we will use the ratio of coefficients telling us there's 2 moles of silver sulfide produced for every 2 moles of hydrogen sulfide that reacts. Okay, once again we see that our unwanted units cancel out. We're left with moles of silver sulfide. Okay, and here we produce 0.38 moles of silver sulfide. So we can see that, okay, we are in a position to determine the limiting reactant in this problem. All right, so now that we know how many moles of product could be formed from each of the reactants, we're now in a position to determine the limiting reactant. Remember, the limiting reactant is the reactant that produces the least amount of product. So when we compare, okay, starting with 125 grams of silver, we determined that we could produce 0.579 moles of our product, silver sulfide. Starting with 13 grams of hydrogen sulfide, we could produce only 0.38 moles of silver sulfide. So we see here that since 0.38 is less than 0.579, that our hydrogen sulfide is the limiting reactant. Okay, why? Because it produces the least amount of product. So our limiting reactant is hydrogen sulfide. Okay, we can then infer that our reactant in excess, okay, the reactant that will be left over after the reaction is complete, will be the silver. So step 4, we need to now finish answering whatever questions are posed to us in the problem based on the limiting reactant. So in this problem here, okay, we are asked to determine what mass of tarnish, that is what mass of silver sulfide, is produced. Now we know how many moles of silver sulfide is produced based on the limiting reactant. We said that was 0.38 moles. Okay, we can then use the molar mass of silver sulfide to convert moles into grams. So the 0.38 moles of silver sulfide times the molar mass of silver sulfide, that is about 247.81 grams per mole, okay, will give us a mass of 94 grams of silver sulfide produced. So we're halfway done there. We've answered one of the questions. Now the other question asks us something about the reactant in excess. It says, what mass of the other reactant remains after the reaction? Okay, so we need to take the additional step of determining how much of the reactant in excess is left over after the reaction. So let's revert back to the flow chart that was given, okay, a couple slides ago here. And I'm going to write this flow chart from right to left, okay, because in a sense we're sort of working backwards from where we started. We're now taking the moles of product formed from the limiting reactant, that is, okay, we said 0.38 moles of silver sulfide could be produced. Okay, and we are now going to use the ratio of coefficients from the balanced equation to figure out the moles of the reactant in excess, okay, in this case silver, that was consumed. In other words, okay, since the silver is the reactant excess, there will be some silver left over, okay, but using the ratio of coefficients, we need to know how much silver was not left over but was actually used up to produce the 0.38 moles of silver sulfide. And of course, once we know how many moles of silver was used up, we can use the molar mass to convert that into grams, to figure out how many grams of silver was consumed in the reaction. So although I wrote the flow chart from right to left, okay, when we perform a calculation, we typically work left to right, at least in this country. So let's go ahead and okay, write this out. We said that 0.38 moles of silver sulfide was produced. That's based on the limiting reactant. Okay, we will use the ratio of coefficients in the balanced equation to see how much silver, okay, was actually used to produce that. So from our balanced equation, it turns out that 4 moles of silver will be used to produce every 2 moles of silver sulfide. Okay. We can then use the molar mass of silver, okay, to go from moles of silver to grams of silver. Okay, notice that our units cancel out, and this tells us then that 82 grams of silver were used to produce the 0.38 moles of silver sulfide. Now we're still not done yet, because the question doesn't ask us, Okay, how much silver was used up? It says how much silver is left over. So we're going to need to perform a subtraction problem here, and we can reason that, okay, the mass of silver that's left over after the reaction would be exactly equal to the mass of silver we start with minus the mass of the silver that would get consumed in the reaction. That's what we just figured out. In other words, we start with 125 grams of silver. We figured out that 82 grams of it would get used in forming the product. Okay, that would leave us 43 grams left over. In other words, 43 grams of that silver would remain untarnished. All right, so let's apply this procedure to one more example involving limiting reactants in order to reinforce some of these concepts. So in this example, we're told that the fizz produced when antacid tablets are dropped into water is often created by the production of carbon dioxide during the reaction between sodium bicarbonate and citric acid. Okay, sodium bicarbonate is a base and citric acid obviously is an acid. Suppose that an antacid tablet is composed of 2.0 grams of sodium bicarbonate and 0.5 grams of citric acid. Which of these is the limiting reactant? How many grams of sodium citrate will be produced? How many grams of each reactant will remain after the reaction is complete? So as always, the first step is to write a balanced chemical equation for the reaction. Now, admittedly, this reaction here is what we would consider to be an acid-base reaction involving carbonates. When we get to our unit involving acids and bases, we'll talk about this type of reaction. Okay, but for now, you're just going to have to take my word for it, okay, to predict some of the products. It turns out that when you have an acid reacting with a base, okay, in an acid-base reaction, okay, the two products that you will always get will be a salt or ionic compound and water, okay, in the form of a double displacement reaction. When you have carbonates involved, another product, okay, is going to be carbon dioxide. So we're given a few hints as to what the products are here, okay, but the sodium bicarbonate reacts with the citric acid, okay, to yield, okay, carbon dioxide, water, and the sodium citrate, okay, is the ionic compound or salt. And we've put the coefficients in so that we've atom balanced this equation. Okay, so like I say, don't worry too much about predicting these products yet. Okay, we will take a look at this in greater detail in our unit on acids and bases. Okay, second step, convert the mass, okay, or moles of each reactant into moles of product. Okay, so in this case, we're given the two reactants in units of grams, so we need to convert them into moles of product. Okay, so as we see, starting with a mass of a reactant, okay, starting with the sodium bicarbonate, we have 2.0 grams. We will use the molar mass of sodium bicarbonate, which we're going to have to figure out. Okay, is about 84.01 grams per mole. Okay, so we're going to divide by that molar mass to convert the grams of sodium bicarbonate into moles of sodium bicarbonate. Okay, and then we are now in a position to use the ratio of coefficients from our balanced chemical equation to go from moles of reactant to moles of product. Okay, so the product that we're interested in here, it says how many grams of sodium citrate will be produced. So let's consider of our three products, let's work with sodium citrate. Okay, and we find out that for every 1 mole of sodium citrate produced, okay, it requires 3 moles of sodium bicarbonate. Okay, we see that our unwanted units cancel out and we've converted everything into moles of product. We do the number crunching and we get about 0.0079 moles of sodium citrate. Let's go through the same procedure, okay, for the other reactant in the problem. Okay, so starting with our 0.5 grams of citric acid, okay, we will once again divide through by the molar mass of citric acid to convert grams of citric acid into moles of citric acid. Okay, we will then use the ratio of coefficients from the balanced equation, which tells us that we get 1 mole of sodium citrate per every 1 mole of citric acid that reacts. Okay, and then finally, doing the number crunching, we end up with about 0.003 moles of sodium citrate. So, okay, on the next slide, we'll go on to step 3 and identify the limiting reactant, but you can see right here, the limiting reactant, okay, must be the citric acid because it produces the least amount of product, right? 0.003 moles is less than 0.0079 moles. All right, so as I was just saying, we have taken a look at both reactants. Okay, we have seen how much of a given product they can produce. Now, we chose the product based on which product we're asked to find information about in the problem, which is the sodium citrate. And we say that the limiting reactant will be the reactant that produces the least amount of product, okay, which we identified as the citric acid. Okay, that makes the other reactant, okay, the sodium bicarbonate, the reactant in excess. So we now have to base our answers on the limiting reactant. Okay, we are now in a position to answer the questions here. So of the 3 questions posed, we've identified the limiting reactant. The next question says how many grams of sodium citrate will be produced? Well, we know how many moles of sodium citrate will be produced. Okay, that's based upon the limiting reactant. So we simply need to convert from moles of sodium citrate to grams of sodium citrate. So we said 0.003 moles of sodium citrate will be produced. That's based on the limiting reactant. Multiply by the molar mass of sodium citrate. Okay, about 258.07 grams per mole. And we now know how many grams of sodium citrate will be produced, about 0.8 grams. Okay, and finally, the last question, how many grams of each reactant will remain after the reaction is complete? Okay, this is not always, but very often asked in these types of problems, okay, to determine how much of the reactant excess is left over after the reaction. So, as we said in the previous problem, let's consider this flow chart. Now that we know how many moles of product will actually be formed, since we've identified the limiting reactant, we can work backwards using the ratio of coefficients to find out how many moles of the reactant in excess would be needed to form that amount of product. Okay, how many moles of that reactant in excess would be consumed, and once we know how many moles are consumed, we could use the molar mass to convert moles into grams. So working from left to right here, okay, we said that 0.003 moles of the sodium citrate would be produced. Okay, let's use the ratio of coefficients from our balanced equation to figure out how many moles, okay, of the sodium bicarbonate, okay, would be required to produce that many moles of citric acid. So we find out that for every 3 moles of sodium bicarbonate that reacts, we will produce 1 mole, okay, of sodium citrate. Okay, and we can now convert the moles of sodium bicarbonate into grams of sodium bicarbonate by multiplying by the molar mass. Okay, and when we do the number crunching, it turns out that about 0.8 grams of the sodium bicarbonate is consumed. So, okay, we can reason that, okay, how much of the sodium bicarbonate is going to be left, okay, is obtained by doing a simple subtraction. Let's identify how much we start with, okay, which is 2.0 grams. If 0.8 grams reacts, then 1.2 grams will remain after the reaction. Now, so that's the hard question. How many grams of each reactant will remain after the reaction is complete? Well, obviously, okay, the limiting reactant, okay, which is the citric acid, will get completely used up in the reaction. So, okay, it's sort of obvious if we understand the definition of limiting reactant that there will be no limiting reactant left okay, after the reaction, it will be completely consumed. And lastly in this video, we'll talk briefly about the yield of a product in a chemical reaction. Now, when we determine the limiting reactant in a chemical reaction, we have figured out how much of a given product can actually be produced in the reaction based on that limiting reactant. That predicted amount of product is what we would consider the theoretical yield. It's the predicted amount of product formed after we do a stoichiometric calculation where we've made the assumption that all the limiting reactant is consumed in the reaction. And I say here, this is what you've been finding in solving the limiting reactant problem. Now we're just going to give a name to it. We're going to call it the theoretical yield. It turns out, okay, for many reasons, that the actual yield, in other words, the actual amount of product that can really be formed in the chemical reaction when all the limiting reactant is consumed, is going to be slightly less than what we would predict in theory. In other words, the actual yield will be less than the theoretical yield. This can happen for many reasons, and I'll mention a couple briefly here, but you will not be tested on this. It turns out that some of the reactants may remain unreacted when the reaction is complete. This can happen because the reactants may never come into contact with each other in order to react, or if they do come in contact with each other, they may have insufficient energy to actually get the reaction to take place. This is a subject of chemical kinetics. Another possibility is that some of the product may be lost, okay, as a result of the reaction, or some of the reactants may actually form other products in secondary reactions. So for many reasons, the actual amount of product you would get by measuring it after the reaction is complete is going to be less than the amount of product that you would predict you would get, assuming that all the limiting reactant is consumed. So when we talk about the percent yield in a chemical reaction, we're now talking about really a ratio or percentage of what you actually get, okay, the amount of product you actually get, which is what we call the actual yield, okay, divided by the amount of product you predict you should get, which is what we call the theoretical yield. And of course, we will turn that into a percent by multiplying by 100%. So lastly, we'll take a look at an example where we'll be asked to calculate the percent yield in a stoichiometry problem. So in this example, we're told that a piece of copper with a mass of 5.00 grams is placed in a solution of silver nitrate containing excess silver nitrate. The silver metal produced as a result of the single replacement reaction has a mass of 15.2 grams. What is the percent yield for this reaction? So as always, we will start by writing the balanced chemical equation for the reaction. Since we are told what the reactants are and we are told that this is a single replacement reaction, we should be able to predict the products. So we have copper metal reacting with silver nitrate. The copper and the silver will change places. Okay, copper being more reactive than silver. And we will put in the coefficients as you see in order to atom balance the equation. The second step is to solve the stoichiometry problem to determine the theoretical yield. Remember, the theoretical yield is the amount of product we predict we should get based on the limiting reactant. So this is what we've been doing this whole lesson. This problem is particularly easy because we are actually told which of the reactants is the limiting reactant. It tells us here that the silver nitrate is in excess. Okay, the 5 grams of copper is placed in a solution of silver nitrate containing excess silver nitrate. So if the silver nitrate's in excess, then we can assume that the copper is the limiting reactant. So we don't need to figure that out. We can now predict how much product will be formed based on the limiting reactant, which is copper. So let's do the stoichiometry problem. Okay, we're starting with 5 grams of copper. We will divide through by the molar mass to convert grams of copper into moles of copper. We will then use the ratio of coefficients to go from moles of reactant to moles of product. Okay, in this case here, we're told that we will form 2 moles of silver for every 1 mole of copper that's consumed. And finally, we can convert from moles of product into grams of product, multiplying by the molar mass. So we look that up in the periodic table and find out that silver has a molar mass of about 107.9 grams. Do the number crunching, and it turns out that our 5 grams of copper, when it is completely consumed, will produce 17.0 grams of silver. So once we know the theoretical yield, okay, which is the 17.0 grams of silver, that is what we predict should be formed by doing the stoichiometry problem. We're now in a position to calculate the percent yield. In the problem, we're told that the silver metal produced as a result of the single replacement reaction has a mass of 15.2 grams. So that 15.2 grams represents the actual yield in the problem. Note that it's slightly less than the predicted or theoretical yield, okay, as it will always be for some of the reasons we mentioned in the previous slide. So when we take this ratio of what we actually get to what we predict we should get and multiply by 100%, we get a percent yield of 89.4%.